Hello everyone. Today I am so glad here to share our paper, BSRT, Improving Burst Super Resolution with Swin Transformer and Flow-Guided Deformable Alignment. This work was done by Megvi Technology and the University of Electronic Science and Technology of China. The source code and pre-trained models are already publicly available. The goal of burst super resolution is to recover a high-quality image from a set of low-quality images. Using multiple frames could alleviate the ill-posed property of super resolution, but there are also several challenges in burst SR task. For example, the inputs are usually noisy, misaligned, and captured in raw format, which can hardly be solved by common networks, making the restoration process difficult. Address these challenges, we propose a new framework named BSRT. There are three main contributions in our work. First, we propose an efficient pipeline for processing raw burst sequence. Second, we design a pyramid flow-guided DCN module for better feature alignment. Third, we introduce the Swin transformer in feature extraction and reconstruction to improve the performance. This is a visual comparison between our method with other approaches on burst SR test dataset. As we see, our method can recover details correctly. There are the performance comparison on both synthetic and real-world dataset. Our method achieves the best performance while being computationally efficient. Our framework inputs a sequence of raw images and outputs a high-quality RGB image. Specifically, given a set of raw burst inputs, we first upscale all frames to one-channel RGB format using pixel shuffle. Then these frames are sent to SPINET to obtain multi-scale flows between each frame and the reference frame. Meanwhile, we extract features from original raw inputs and upscale them before alignment so that we can combine the pre-calculated flows with DCNs on multi-scale features in the Pyramid FG-DCN alignment module. After that, we fuse these aligned features by a conva layer and restore the final HR image through several Swin transformer groups. And each Swin transformer group consists of several Swin transformer blocks and a conva layer. Note in our approach the raw processing pipeline is different from the previous EBSR. In EBSR, the raw inputs are first flattened to one-channel big feature maps and then we perform all operation on the large features. Such a strategy improves the performance but is computationally expensive. In practice, we have noticed that the performance improvement mainly comes from performing alignment and reconstruction on the large size feature maps. Address it. We modify the pipeline to that the feature extraction is applied on the low-resolution space, and scaled 2 times before alignment. Compared with EBSR, our approach is effective and computationally efficient, and thus can use a larger patch size and batch size to accelerate training. Now we illustrate the flow-guided DCN alignment module. Given inputs feature 1, feature 2, and the corresponding flow estimated from the SPINET. We first warp feature 2 using flow to get a coarse-aligned feature 2. Then we concatenate this coarse feature with feature 1 to obtain a refined offset, which can be added with the flow to get an accurate offset. And we obtain the final aligned feature 2 based on the DCN. Moreover, we design a 3 levels pyramid structure to further improve the alignment. From level 3 to level 1, the predicted offsets and aligned features are upsampled and subsequently concatenated with the next level's offsets and aligned features. By doing so, we can refine the output feature with multi-scale information and raise superior to noise reduction. In the experiment, we evaluate our method on 2 datasets, synthetic dataset and real-world dataset. The scaling factors are fixed to 4. Here we show the quantitative results and the number of parameters of each model. The proposed method, even the efficient one, BSRT small, can achieve good performance on both synthetic and real-world datasets. Moreover, we add an ablation study to illustrate the effectiveness of the main components of the proposed BSRT, including the new raw processing pipeline, Pyramid FG-DCN and Swin transformer blocks and groups. This slide shows the visual comparison on synthetic dataset. As we can see, the proposed method is robust to artifacts and able to recover rich details, even noise-like textures. There are visual results on real-world images. Our results are clear and visually pleasant. In conclusion, we propose an efficient pipeline for raw burst super resolution task. We propose a pyramid flow-guided DCN module which uses pyramid flows to guide the DCN to align features with multi-scale information. We introduce the Swin transformer in the feature extraction and reconstruction, which can further improve the performance. The proposed BSRT achieves an ART performance in burst super resolution. Thank you for your attention.